I'd like to introduce myself. My name is Prof. Hamprecht. I've been in Heidelberg for a long time, since well, 2001 in fact. And for the first few years in Heidelberg, or for the first many years in Heidelberg, I was working in machine learning for image analysis, for computer vision. And last year, decided to switch gears with the entire lab. And I'll tell you what my lab does in a minute, but first I wanted to put the header for it, so the title of the lecture. Okay, so for my lab, I think I have a new logo. The new logo is as follows. Where are we working? There was a Nobel Prize for Chemistry in 1998 for the development of density functional theory. There is a Nobel Prize for Physics. You've all heard it this year. Well, in my lab works here. I'm not sure if that is a good sign or a bad sign. Yeah? I could argue, you know, we missed the mark, or I could argue, yeah, there's something going on here. All right, so this is my lab. We call ourselves Scientific AI, and we use machine learning to solve problems from natural sciences, in particular from this density functional theory, which is a part of quantum chemistry. And towards the end of the year, I will, towards the end of the semester, I'll tell you a bit more about what that actually is. And well, the reason I stuck around at university for so long, and at this university in particular, is because when people ask me what's the best thing about Heidelberg, I tell them it's the very good students. So it's you know, very, very smart people, and also many kind people, and that's a real pleasure to have been working, you know, with your predecessors for all these years. Yeah. So this lecture, what are the learning goals? This machine learning in physics, it's a bit of a dual thing. There is, on the one hand, the physics of ML, and there is, on the other hand, the ML4 physics. And I think, so I'll try and do both, but to be honest, I think the emphasis will be on the second point here. Because many machine learning methods are inspired by physics, so there are physical concepts or physical models or physical equations in there. But then usually the thing that works best in the end is not necessarily the pure physical model, but with some additional tweak. And well, these most powerful models that we have nowadays, they of course make a huge difference for the sciences as a whole, and for physics in particular. A word about the curriculum. So we will have a when deciding what to put in the curriculum, it's a mixture of I would say 2/3 or 3/4 of concepts which I consider timeless, at least on the scale of machine learning. So where it's really about understanding things, and the remainder is about relatively recent developments or architectures that may change from year to year. And in the old days, there was this dichotomy of there was unsupervised learning, and the lecture is going to be mostly Blackboard, but occasionally I want to show you some picture. And picking up first picture here is one example of work in unsupervised learning. And this all right. So you see this is the work of Sven Peter and Elke Kirschbaum. He used to work here. Sven was a physicist from Heidelberg, Elke a physicist from Tübingen. And Elke has returned to Tübingen, where she's working for Amazon. So the task that they worked on was the following. A problem from the neurosciences. You see traces of, in this case, 20 neurons. And these are not the kind of neurons that we have in most neural networks today, but these are spiking neurons. So occasionally you have a blip when one of these neurons spikes. And at the time we were working with neuroscientists to try and make sense of such traces. And well, in this field, it's very difficult to come by any form of ground truth. So you don't know what the true solution is. So in this case, we simulated this data. Yeah? This data we made ourselves, and we know what the ground truth is. Namely, so from left to right is time, and there are these ground truth motifs here. And so there's this motif, it only involves neurons 1 through 5, and this firing pattern, and there's that motif and that motif. And from combinations of these motifs plus noise, we constructed this data. And then the task was to try and infer the motifs. And of course, there is no natural ordering in the motifs we extract, but we've sorted them nicely such that the first one actually corresponds to the first one, second one, the third one to the third one. And then there were also noise motifs that we picked up. And that was one example of unsupervised learning, which I quite liked, because, well, when you look at that, it's difficult to come up with a notion that all of this is a combination of just a few motifs, and it's actually possible to find these. So that would be one example of a typical unsupervised learning task. And then, of course, the mainstay of machine learning has been supervised learning. And I've taken one example here from the work of Tilman Plain's lab. So the machine learning landscape of top taggers. And well, what you see here is one particular signal, and then averages over 10,000 signals in case there really was an event and in case there was not an event. And in supervised machine learning, you get lots of training data with a true label, and then given any new observations, you try and predict that true label. All right, and for the last many years, so there was this spectrum of unsupervised learning and of supervised learning. And this has always been a continuum, but for most methods, it was easy to say whether they are rather on the one or on the other end of the spectrum. And in particular, the community was most in love with supervised learning. And I would say this is changing or has changed with generative AI. So with these methods that generate images, or in particular text or music. And I think I would put them more on the side of unsupervised learning. And those amazing large language models with their amazing capabilities, all this, well, that's part of generative AI, and that's more on the side of unsupervised learning. Speaking of which, GPT and the likes, I use it a lot, and I would encourage you to use it a lot in learning, in doing your exercises. But the important thing is really that it helps you learn. If you walk this way, you'll be on video on YouTube. The million viewers will see you come late. All right. So the important point is to use it to help you learn and not to replace you in, just, yes, you can use it to hand in a solution and that will be fine, the solution will be fine, but you will not have learned anything. Yeah? And the thing is, of course, that if you want to not just use the techniques, but understand them and master them and be able to maybe change them in the future, then you need to be able to look under the hood. So for example, Leonard, one of our master students, he's interested in those models a lot, and he has done super nice work on detecting if a large language model lies. And this work, incidentally, I think I will talk about it in more detail at some point, is going to be presented at NeurIPS in a few weeks' time. That's one of the 3 biggest conferences in machine learning. And if the models are lying to us or if they're hallucinating and so on, that's an important question. And this kind of question you're only able to answer if you grasp the concepts and don't just parrot what they're telling you, of course. Okay, so the learning goals of this lecture are to see physical concepts in ML, and in particular to be able to use ML to solve problems from physics and elsewhere. And I will continue with a tiny bit of survey of where the field stands today before actually starting with the contents of today. So just where does the field stand today? We now have, of course, this boom of AI, and I just wanted to recall that there have been, summers and then so-called AI winters before. I cannot even write history because I'm only going to talk about the summers for now. So the first one was in the late 50s, and the thing that caused a sensation at the time was the perceptron. So the first summer was the perceptron, which is a single neuron of the kind which we have in our neural networks today. And this was briefly after World War I. It was a machine that could learn in an unsupervised fashion, and people were blown away by it. The first winter came when people realized that the perceptron can only solve linear problems. So, in other words, in supervised learning, you often see pictures like these. We have 2 classes here, and you would like to learn some decision boundary. And here, the decision boundary, the optimum one would, I don't know, perhaps look something like that. But perceptrons could only do linear. And then people were very disenchanted and fell out of love with the field for some time. Then there was a second summer. This was, I would say, in the 80s, when people figured out, okay, a single perceptron can only do linear, but if we combine many of these and give them nonlinear activation functions, then we can build multi-layer perceptrons. So there was that, and there was the backprop algorithm. This was late 80s. And again, people were very excited about it, people being mostly electrical engineers who worked with that at the time. And well, it eventually faded when it turned out that these things were very hard to optimize. So second winter was the realization that, well, these methods, it is not easy to make them solve real-world problems. So a famous example from those days was, it's not totally clear whether this is a true story or not, but supposedly one of these systems was trained to find tanks on pictures. So tanks, the military instruments, and then it seemed to work great, and then it failed abjectly, and then the reason was found to be that after the fact that, well, all the picture on the training data, all the pictures with tanks had the sun shining, and without the tanks had less nice weather. So it basically learned to say, you know, is the sun shining or not, and not is there a tank or not. So again, disenchantment and too much hype before, and then it suffered. And then I'm probably forgetting some more summers and winters, but the third summer, I would say, is now. This started in 2012 with AlexNet. This was a neural network for image classification, which completely blew all performance benchmarks that people had been working on for years. So people had developed very complicated, very sophisticated architectures, non-neural network architectures, to recognize content in images. Very clever work also on the side of optimization. And then along came one student by the name of Alex, with one advisor by the name of Hinton, the guy who now won the Nobel Prize. And not building on decades of refinement of models, they just achieved accuracy that was previously unheard of. All right, so that was 2012, AlexNet. And then a bit later came AlphaGo. So chess had been solved in the sense of a computer being better than a human sometime in the early 2000s. Or was it late 90s? Anybody knows? But Go had a significantly larger search space and was a harder target to crack than chess. And then AlphaGo did, by means of reinforcement learning, that was a real success. And then came nowcasting, still going on. So, you know, predicting weather accurately. And then finally, crowning achievement was this AlphaFold. So to predict the structure of proteins based on their sequence. This had really been a long-standing scientific problem, and one which this year then received the Nobel Prize for chemistry. So superb achievements. And well, why? You know, why did it work now and not previously? There's not a single answer, but compute was really important. Then training data was really important, because in those days, the internet did not exist. Yeah, so even if you had the compute, you would not have had the data to train it on. And now the internet does exist, and you can just get, you know, oodles of images and libraries full of electronic text to train on. Sadly, I'm only putting in the third place here ideas. Yes, they are important, but I think that the two first have been more important. And yeah, combined with ideas, I would call it experience. So it's empirical knowledge that, you know, some activation function works better than others. And then whenever one activation function works better than others, then eventually people come up with theoretical papers of why is this activation function better, but that tends to always be after the fact. Yeah? So first they find the more, you know, useful activation function, and then they explain. That's a bit sad, but you know, maybe this is how it often goes in science. All right, and my handwriting is bad to start with, and when it gets too small, people in the rear, you know, give me a shout. Okay. And this summer, so the question is, when is the next winter? Now this is open for speculation. I don't expect the kind of winter that we've seen before, because, well, basically these systems now, the large language models and the like, they work so well. It is difficult to see them go away unless our civilization collapses completely or something, you know, dramatic happens. So I don't see it going away anymore. The question is more, what will it morph into? What will it become? What will it do with the society also? Okay. And I wanted to, give one viewpoint. That's the viewpoint of Chris Bishop, who is a physicist by training, and he has been a really important formative figure in machine learning. He is now head of scientific AI, or whatever it's called, at Microsoft. And he postulates a fifth, okay, I want to write larger, a fifth paradigm of scientific discovery. And by his counting, the first paradigm was just systematic observation. So when we heat water, it starts to boil. Or if we hold an apple and we let it loose, it drops. Okay. Secondly, and that was the huge jump, was this codification in natural laws. So I would say, let's call this the mathematical formulation. Natural laws. So no longer the apple drops, but force equals mass times acceleration. And that was this took a few millennia and was a huge jump in level of abstraction. Millennia is probably an underestimate. Yeah? If we say humans like us have been around for, order of 100,000 years or so, well, it took 99,000 out of the 100,000, to go from here to there. Then there was still much more recently the ability to solve these laws in non-trivial cases. So numerical computation. This started with human computing or with analog devices in civil engineering and such, so the construction of bridges, etc. Also in the military, to compute trajectories of projectiles and such. Let's say this started in the 19th century. So this part I think has been forever. So since humans have been around. This one here is, since Newton or so. Let me put here 1700s. The numerical computation, let's say analog, has been in the 1800s, and with computers in our sense, started essentially with the computations that were required to build a nuclear bomb. So unfortunately, many of these developments, as you see, they were somehow engendered by military activity. So let's say this was 1940s. Using the kind of computers that we have now, not using transistors yet, but still proper computers. Then, by his counting, the fourth paradigm has been data-intensive scientific discovery. And what he means by that, I believe, are accelerators, the observational instruments that we have in astronomy. So in any case, devices that require digital storage of the observations and then allowed to mine these observations. And I'm putting here, maybe 1980s, maybe later. And by his account, this is now maybe the era of a fifth paradigm of scientific discovery, where, in his words, the idea is to train neural networks to predict rather than compute solutions. And the beauty here is that thanks to number 3, it is possible to generate infinite amount of training data. Yeah? And on this infinite amount of training data, you can then learn to predict solutions. And I mentioned nowcasting. Yeah? So for the weather forecasting, traditionally, you would integrate differential equations. And that works pretty good as far as we know. But it has, of course, its limitations, some which are impossible to overcome, like turbulence and the fundamental chaoticity in the system. But some of the limitations are because we make assumptions. Like a medium, we assume it is incompressible when in fact it is a tiny little bit compressible and so on. Yeah? So we typically have assumptions in this modeling, and these assumptions do not necessarily go into the training of neural networks. In particular, talking about the weather again, if we train this on massive historical data, then one can do that without starting from any prior assumptions, really. And if we, all right, and this, I would say, is only starting to become possible now, let's say the 2010s or so. In the language of optimization, or often this entails optimization problems, this is step number 3 here, that would be classical optimization. And number 5 here is something that I would call amortized optimization. This is not a term that I'm inventing. It means, oh, this is totally unreadable. It means that we are directly predicting the solution of an optimization problem. And where does this word come from? It means we make an investment up front, in this case, the very expensive training, to later make life easier for us. Okay, and overall, these are the ideas of Chris Bishop, who has also written a nice textbook, by the way, which is available on the internet. It is called Pattern Recognition and Machine Learning, or PRML for short. And it is nice, but it's not the primary textbook that I'm recommending, because it is a little bit too Bayesian in spirit. So what do you mean by too Bayesian? Yes, Bayesian viewpoint is great, but there are some techniques, like the ones that we will spend the rest of today on, that are not Bayesian, and or it's very artificial to interpret them as Bayesian. And Bishops go so far to, simply not mention it at all, because it's not proper. And well, I care more about what is useful than about what is Bayesian. Yeah, and so this is what I mean by, I think he's sometimes a little bit too Bayesian. Good. So this is a very broad view of where we stand today. And in terms of what's actually going to happen in the lecture, there is a website, which probably many of you have seen. And on this website, it's not detailed to the level of individual weeks, but it broadly explains what we're going to do this semester. Namely, we will visit unsupervised learning, supervised learning, and things in between, notably also the generative AI. And it is difficult to bring that into a one-dimensional sequential order of lectures. So what I'm going to do is I'm going to meander a little bit. I'm going to do unsupervised learning and then supervised various concepts, and then returning to unsupervised and generative in the sequence which I found most natural, which I hope after the fact you will find acceptable or accessible also. Okay. I will make some comments about admin stuff at the end of today. Other than that, do you have any questions so far? Anything you would like to discuss? Yeah. Yeah, where's this website? So, okay, I can try and display it properly. I know the beamer is not on yet. All right, this is the website of our lab. And somewhere is teaching, and there is this course, and there is this curriculum. And I am pretty sure by now that the clustering I will move down in the order because when talking about large language models and so on, I might need more time than is foreseen here. And if I have to sacrifice anything, then I think I would sacrifice the clustering. But broadly speaking, yeah, this is the plan. Any other questions? Yes. Required? So you're a computer scientist? Yes. Yes. I think you will be fine. So we might have a differential equation occasionally, but not in the majority. So I think this will be fine. Yeah. Oh, a bishop. Yeah. Mm-hmm. Yeah. Okay. Any other? Yes. If you have some very good numerical model that can produce good data, and it's already fast and efficient enough to generate a lot of it, why would you need to train a new model? Yeah, I think you all heard the question. If we already have a very good approach 3, why go to 5? And the reason is that they are still not fast enough. So if you look at, so we spend a fair amount of energy on compute. So sadly, we hear that a nuclear power station is again going to be spinned up. just to generate electricity so that we can use GPT. And so overall, supercomputation is a very energy hungry business. And then you can look at a breakdown of where does supercompute time or energy go. And around 15% or so goes just into weather forecasting. And so if you translate that into CO2 production and so on, this is enormous. And well, the thing here with this amortized optimization is that training it is super expensive, but once it is trained, the inference can really be cheaper than doing it the classical way.